The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Good afternoon. My name is Joe Levitt. My group members are Ben Ayton, Jess Noss, Eileen Harvitz, Jake Barnwell, and Sam Pinto. And we're going to introduce you to the topic of incremental path planning. Listed on the screen now are just some of the references we used in putting together this lecture. The top three are the main references we used in developing our material on the D Lite algorithm. But also take note of the bottom reference, which is a paper done within Professor Williams' group here at MIT that talks about all pairs, shortest paths, incremental search method. So if you're interested in more incremental search methods than those we're going to talk about today, please get into this, especially if you're going to go ahead and do our piece set. These references will be very helpful to you. So today we're going to first motivate the problem, then we're going to introduce the idea of incremental search, then we're going to go into detail on the D Lite algorithm, which is a type of incremental path planning, or an algorithm used for incremental path planning, run through an example of D Lite, talk about when it is good to use incremental path planning, when other path planners might be better, and then go into some algorithm extensions and related topics and some applications in mobile robotics. So in order to motivate the problem, we're going to use a robot living in a grid world. It's at a start location, trying to get to a goal location. It can move up, down, left or right or diagonally, and it can only see the 8 cells around it as it's moving through this grid world. And we're going to give it some predefined map of the world. This is the map it has of the world before it starts moving. And it's possible as it's moving through that some of these new obstacles could appear, or obstacles could go away. And the idea is that it's going to make observations as it's moving through this world and update its plan to get to the goal based on what it sees as it's moving along. So I must correct myself. Sorry, the map that you're seeing now is the map that the robot has ahead of time. The previous map is what the environment actually looks like. So as it starts moving, it's gonna make a plan to get from the start to the goal. That's what we want it to do. And then it's going to move to the next position and then realize that there's an obstacle in the path that it previously planned, and now it must replan in order to find a valid path to the goal. And so now it replans and continues to move on the new plan, and now it finds another obstacle that it has to replan around and does the same thing, and then continues to walk through until it gets to a point where we have a change in the environment. Change is represented by these two cells going black here. And now its original plan is no longer valid again. And what we want it to do is to replan to find a new valid optimal path to the goal. This is just showing here what happened to our environment. And then the robot replans and continues to march towards the goal. So this is the behavior we want from a mobile robot, whether it's a two-dimensional path planning problem or we're talking about multi-dimensional robot arms planning, working with humans in a manufacturing environment, or an activity planning process. The idea is that we want the robot to be able to account for new obstacles or changes in its representation of the environment and continue to plan along the fly quickly and optimally. So there's methods that accomplish this. One method used in path planning is rapidly exploring random trees, or RRTs. RRTs are basically going to replan on every time step based on changes in the environment. And one problem in my experience here, though, is that RRTs are suboptimal, even though fast. So here you see the robot has come up with a plan, it's seeing new obstacles, the table in front of it, the coffee cup, and it's planning for those things, but the plan it came up with is clearly not optimal. So we can perform some additional computation. We can use a method that builds upon the RRT star that finds an optimal path, but that requires a pretty significant amount of offline computation time. And then you can accomplish something that looks a little more normal. But again, we have to allow the robot to perform a lot of computation offline. So how do we accomplish what we want to? We want to compute quickly, we want to compute optimally, and then have the robot continue to move as it's receiving new information from its environment. So the problems we're facing, there's changing environmental conditions, we have sensor limitations, you might not be able to see everything in the environment around you, and then we have limited computation time. And the solution that we're going to explore here is to reuse data from the previous search in order to speed up the search process and continue to plan optimally. And the method we're going to use to accomplish this is incremental search. So now we're going to talk a little bit about what incremental search means. First, to show you kind of how powerful incremental search can be, this is one example of an incremental search method, incremental all pairs shortest paths, which allows you to online compute paths between any start and goal location. The idea is that you have a robot that's trying to move around one obstacle, that's what you see in the upper sequence of events there, and then another obstacle is added, and now it has to plan around this new obstacle. And using this algorithm, you have a significant increase in performance in computation time using the all pairs shortest paths versus an RRT. RRT Connect is another version of an RRT where you're planning basically from both the goal and start and connecting your paths. It's on the order of what you get with RRT, but this RRT Connect algorithm doesn't give you an optimal result. And then it's even faster than another algorithm, probabilistic road mapping, where you're randomly sampling the environment and connecting points to produce a path. So the idea here is that we can really leverage this idea of reusing results from previous searches to accomplish fast replanning online. So the whole idea of incremental search is that we're going to perform a normal graph search, just like anybody's used to, and then we're going to repeat as the robot moves through the environment, or you're executing your plan. You're going to execute the next point in the plan, or the next action in the plan. We're going to receive changes from the environment, either through our sensors or information provided from the outside. And then we're going to use that information to update our previous search results instead of completely replanning, and then continue to perform that loop until you reach your goal. So before we get into too many of the details of how we're going to accomplish this, first we want to review the graph search problem. So in graph search, you have a graph consisting of vertices or nodes. We're going to use nodes throughout this lecture to talk about the vertices or nodes in the graph that are connected by edges. And then there's an edge weighting function that describes the cost going from one node to another. And then a heuristic function that describes the cost, or is an estimate of the cost to get from a current node to the goal node. And then we have a start vertex and a goal vertex. In the graph search problem, we're also going to have this idea of a g-value, or a cost so far. We're going to use the term g-value, which is essentially the cost that it's taken to get to some predecessor node plus the cost to the node that you're actually expanding. So from you would have this W start to S1 cost to get from start to S1, and then the G value for S goal would be the weight from S1 to the goal plus the S1's G value. And then yes, go ahead.
What is W?
W is the weighting function that I talked about previously here. So the weighting function describes the cost to get from one node to another along any edge in the graph. And then we use those weighting functions to develop the idea of the G value. So W is just the cost of the edge cost. And then our heuristic value, we use our heuristic function to establish a heuristic value from one goal to another, and we're going to call that our H value, or H. And then the total estimated cost to get from a node that we're currently expanding in a graph search is F, which is your cost so far, plus your estimated cost to go. I think I might have messed that up in there. G value associated with cost so far, not cost to go, and then H is an estimate of cost to go. So in order to reason about a real-world environment, we first have to take that environment and convert it to a graph so we can form graph search and then do everything we're talking about. Some of the examples we're going to talk about and some of the ones we've already talked about, we're using this notion of a grid world. You can have a four-connected graph or grid where a robot can move up, down, left, or right, basically in X or Y directions, or an eight-connected graph where you can also move along the diagonals. And then here we just show the graphs associated with those, with the nodes and edges. And then you would have an associated admissible heuristic with those if you're going to perform a heuristic search. So just know up front that at any time we're moving from a real-world environment that we're trying to reason about with these search methods, we have to develop an associated graph. And one more thing that is important as far as understanding incremental search is the notion or idea of relaxation. We're going to use Dijkstra's algorithm. Everybody here familiar with Dijkstra's algorithm? I've seen it in the past. We're going to use Dijkstra's algorithm to kind of illustrate the idea of relaxation, remind everybody of what that means, because it's an important concept when we're talking about incremental search algorithms. So essentially in Dijkstra's algorithm, it's a single source, shortest path algorithm, a best first search. So we're going to be expanding nodes according to their best G value, or cost so far. And we have our start node initialized to a 0 cost so far because you're at your start node haven't occurred any cost. And then every other node is going to be initialized to infinity. And the idea is we're going to find the shortest distance to all of the other nodes by relaxing the cost to those nodes from infinity down to their actual shortest or lowest cost value. So we start with by expanding the start node, and then you find the cost to go, or cost so far to each of the children nodes of the start node. So you have an edge weight of 1, so you have the node on the bottom has a value of 1. Similarly for the middle node at 5 and the top node for 3. Now the next node we're going to expand, can anybody tell me what the next node we're going to expand based on performing best first search here, using costs so far?
The
G value?
1?
Yes, so the node labeled 1 here that has a G value of 1 is the lowest out of 1, 3, and 5, and infinity. So we're going to go ahead and expand 1 next. And now we find that using this value of 1 plus 3 equals 4, which is less than what we previously had here as 4. So now the center node has been relaxed from a value of 5 down to 4. So now the lowest, or the shortest path we found to the center node is 4. And we're going to continue to perform this by going through each node in order from lowest cost. And similarly, you saw how the top node was relaxed to 6 by going through 1, 3, and 2, whereas previously it had a lowest cost of 7 going through 3 and 4. And if we perform that through the whole graph until all nodes have been expanded, then we've relaxed every node in the graph to its shortest path value. And then we can just do a greedy search from a chosen goal node back through the graph to find the shortest path.
Yeah. Just a quick comment.
Yes.
Is the term relaxation standard, or because it seems to me, I mean, the fact that you're bringing numbers from infinity down to a small value sounds more like a tightening as opposed to relaxation. So I was just wondering if people use this as like a standard.
I'm not sure if it is in all areas, but I have seen it in multiple places when you're talking about graph search, specifically with respect to Dijkstra's algorithm. This concept of that is where the term relaxation is used. Okay. And we're going to use that as we go throughout, talk about incremental search, and when we're kind of repairing the results because of new edge weights and things like that, we're going to figure out which nodes we have to relax back down to their shortest value to be able to find the new shortest path. So that's the term we're going to use here. If it's not used universally, I can't say for certain, but we will use relaxation to talk about reducing, it's kind of related to think about like a tension spring. As you have it, as you reduce the constraints on it, it'll slowly relax to its completely relaxed position. That's kind of the idea here. So now that we have talked about the ideas of relaxation and graph search, how do we reuse the results from a previous search in a new search to be able to do this, employ an incremental search method where you have done a search, you found the shortest path, and now you had some changes to your graph, and you want to use your previous results to come up with your new shortest path. So the way we're going to do that is we're going to store our optimal results from a previous path, from a previous search. This can be done in every number of ways. It's going to depend on the algorithm. But you can store like a list of shortest paths, as in an incremental all pair shortest paths problem. The one we're going to talk most about is storing G values, and that's what's done in the D Lite algorithm, where you're finding the shortest distance from any given node that you've expanded so far in your search to the goal node. And then you'll use that data to find your shortest path. And then when you go to form your next iteration, you'll look for inconsistencies in that graph. And then in order to find a new shortest path, we'll leverage that previous data and the inconsistencies, perform relaxations to come up with a new optimal solution. And that's all we're showing here on the right side of these three graphics. Is you have an initial search, you have an obstacle that is now in a place that wasn't there previously, which causes you to update edge weights in the graph associated with this grid world. And then using these values, which represent the G values in the graph search, you update the ones that you need to, only update the ones you need to update to find the new optimal path, instead of completely reperforming our search. So what incremental search methods exist? Now that we've kind of talked about what they are and what we can do with them. So the whole idea of this slide here is to show you that the incremental search can be used across many domains. It's not just specific to path planning. It's used in temporal planning to determine temporal consistency. It can be used in propositional satisfiability to instead of every time you're trying to determine or updating another algorithm, you can use your previous results. And but one we're going to focus on today is D Lite, which is specific to mobile robots. But the ideas and concepts we're going to talk about there are applicable elsewhere, and you can use to help you learn about and expand your knowledge in other areas of incremental search. So the D incremental path planning approach, the whole idea behind it is that we're going to take the idea of incremental search that we just talked about, and we're going to combine it with heuristic search, which gives us an optimal solution. And the idea is that these two things are to some extent are orthogonal, so that we can combine them, and then we can form efficient incremental path planning, getting both an optimal result and quickly getting a new path when things change in the environment without having to completely replan. And so what that looks like, if we have a grid world, which is shown in 4 instances here up on the board, and we're trying to plan from a start node to a goal node, and shown in each of these sections. And in the upper left, or on the left axis, we have whether we're performing a complete search or an incremental search, and on the horizontal axis, whether it's an uninformed search or a heuristic search. So the upper left is a complete search, just using breadth-first search, no heuristics, and what it's showing is all the nodes that are expanded and trying to find a path from the start to the goal. In the upper right is a heuristic search, A*, and employing the heuristic, we're able to collapse the number of nodes expanded by quite a bit. In the bottom left is a incremental search method that's using uninformed search or breadth-first search as an underlying search algorithm, so it's going to expand the same nodes as the breadth-first search. And then in the bottom right, you see a incremental heuristic search, the lifelong planning A* algorithm, which is kind of the baseline for the D Lite algorithm we're going to talk about, that on the initial search will expand the same nodes as the heuristic search, since it's using A* as its baseline. And then, so now, let's say the robot moves, we get an update to the environment, there's a bunch of changed edges. And now breadth-first search, as you can see, is going to have to expand pretty much the same number, if not more nodes than it did on its previous search. And A* also is going to expand about the same number of nodes as it did previously. The incremental search method, using breadth-first search, by using the previous results, reduces significantly the number of nodes that need to be expanded. And then lifelong planning A*, the incremental search plus the heuristic search, reduces that number by even more. So you only have a very few, even with quite a few changes in the environment, you have very few nodes that you need to expand on the next search in order to find a new optimal path. With that, I'll turn it over to Ben to talk about the D Lite algorithm.
Thanks. So I'll be walking you through the D Lite algorithm today. Now, it's worth emphasizing that D Lite is not the only incremental algorithm, as we mentioned previously, but it is a widely used incremental algorithm. And you can see it's quite efficient at what it does. D Lite is an algorithm that searches from a single start node to a single goal node. But as we see changes that occur in the path along the way, we'll adjust them. So it's nice to think about D Lite from two perspectives. One is to think about it as a modification of the principles of A star. Now, you'll see that D Lite in its first iteration or its first run through before any modifications behaves very similar to A star. And that's where it's nice to keep that mental model in mind. And you'll see that in an example further on. With the second perspective to look at A star with is from the perspective of Dijkstra's algorithm, from which we see many of the principles of relaxation that we covered beforehand. From this perspective, we see that when we do reparations to the graph, or changes to the graph, our methods of repairing the graph is essentially to relax down our changed edge weights until they reach their truth. Now, where we differ from Dijkstra's algorithm with something like D Lite is selecting only the nodes that we want to hit efficiently. So whereas whereas Dijkstra's algorithm travels through the entire graph, we only want to travel from a single start node to a single goal node. And so D Lite behaves like Dijkstra's, but a guided Dijkstra's. So I'd like to just remind you of several concepts from A star first, because it's easier to introduce them in that context, and then we'll modify them a little bit. So Joe mentioned before that for A star, we're searching from a goal start node to a goal node. And we're sorting the nodes in our queue by a total cost, which is the sum of what we're calling G, which are our cost to go, or cost to get to a single node, and our heuristic, which is a cost to get from a node S to the goal node, here S. Now, what we don't usually consider with A star, but is very important for D star, is how we distinguish between ties, when two different nodes on the search queue have the same total cost. So here what we're doing is we're introducing a couplet, which consists of two values. The first, which I'm calling F1 here for any given state, is the same as what we're usually used to. It's the linear combination of your cost to reach a node and the heuristic function. But we also introduce a second value for this couplet that's used in the case where only those two draw. And that is simply the cost to go, that G value. So in order of expansion of nodes from the queue, we'll order them in terms of F1 first, and then if two nodes at the front of the queue tie in terms of their F1 values, we select the node with the lowest G value. So, looking at our graph down here, we're looking at our states S1 here and S2 here. Can anyone tell me the total cost for our state, or our node S1, which remember is a couplet of two different values?
$5.3.
So 5, yes, is our cost to reach this node 1 plus the heuristic, which is 2 here. And also 3 is our second value, because it's only our G value there. And so what would the value be by the same logic for S2 down here?
5.2.
5.2, that's exactly right. And so bearing in mind what I told you before, which do we take off the queue first?
S2.
That's exactly right. Because the first value, F1, for these two nodes is exactly the same, but the second value is lower for FS2. I'd also like to introduce the concept of successors and predecessors of any given node. In general, a graph consists of directed edges. And we can have a graph with undirected edges, but we can think of that as just any edge being directed in both directions. So here we define the concept of a successor of a node, which is every node that can be reached from a given node along edges that connect from it. So the successors of this given red node are these two blue nodes here. We also introduce the concept of predecessors, which is every node from which that node can be reached, meaning nodes from which we can follow a directed edge to our node. So for our red node, the predecessors are these two nodes. What I'd like to emphasize here is comparing the two, that this node here was both the predecessor and the successor of our red node. And that's fine. That occurs when we have undirected edges or edges that are directed in both directions. So think about D Lite in the sense that it is a repeated best first search, which is where the A-star principles come in, through a graph with changing edge weights as that graph is traversed. Meaning that as we travel from our start node to our goal node along a path that we are planning, we can see that edge weights are changing. And in this example, I'm modeling an obstacle coming in place between this node here and the goal node, which means that we have removed that edge. And that's effectively the same as changing an edge weight. We're just modeling it as changing this edge weight to infinity, which means that edge can't be traveled along. And as I mentioned before, we can also view this as replanning through relaxation of path costs. So once we have moved to this point, how do we find the path from here to here when this edge has been removed, essentially? So we want to make D-star Lite efficient, and it's a repeated search through the graph as we traverse it. So you'll see that since we're using these G values, if we maintain a formulation where we're measuring the distance to go or to reach a node from our start node, this is not preserved when we move our start node. And we move our start node when we're updating the position of our vehicle. So I see that we show this through an example here. The G value or cost to get from our start node to our current node S here is the combination of these two edges, and so it sums to 4. Now when we move along that path that we've planned to this next node, the G value to get to that same node is here too. And so this isn't preserved. And that means that we'd have to potentially reformulate things on our queue, which would be very inefficient. So what we do is we reformulate our search. And it's perfectly valid to reformulate our search to search in the opposite direction. We're essentially measuring for our G values now the cost to reach the goal from a specific node. And instead our heuristics then measure the costs to get from the specific node, or to get from the start node to our specific node. And so we search from the goal backwards through the graph. In this case, we see that regardless of whether our start node is, we preserve our G values, or our cost to travel from S to that goal. So that's what we like, and we will keep that reformulation to maximize efficiency. So here I want to give you a kind of overall understanding of the D-star Lite algorithm before we dive into the specifics of what it's doing. Firstly, we want to initialize all nodes as unexpanded, and what exactly it means to expand a node later, I'll cover. And then we're doing a best first search from the goal node to the start node until the start node is consistent with its neighbors. And I'll again say what that means later. We then move our start node to the next best vertex, essentially moving along the plan, moving along the plan that we created. And then we have to see if any of those edge costs change. We track how our heuristics change, and then we update the source nodes of those changed edges. And we essentially repeat this process until again we've converged to a solution and we keep moving. So this best first search, the A-star Lite part of the algorithm, is where most of the computation is going to be occurring. However, the incremental component is actually how we adjust our edge costs to make sure that we're using most of the information that we previously gathered as efficiently as possible. So I'm going to walk you through various steps of this, but first I'd like to walk you through this step of moving to the next best vertex, just so you understand that well. So we can extract a path, given the path costs that we have, through this simple argument, which says that we map the successor, by which I mean we restate what the start node is, because we're moving from one state to the next state, which becomes the new start node, by this formula, which essentially says that we're taking the best path in the sense that we're minimizing the total cost that would be gained traveling by that path to this node. So in essence, the G value to get to this node, to the red node from the green, recall we're searching back through the graph, by this path here is 7. But to get to this node from the lower node is 10. And so our G value that is optimal is 7 in this case, and the node that we pick as the successor is the green node up here. So now to walk through some principles that appear in both of these steps. I want to show how we handle weight changes locally. And we do this because we don't want to track weight changes throughout the entire graph. We want to handle this efficiently and separate them, so we only need to handle the changes that really impact our problem. So this is the same formula that defines our successor, or our G values for a given node. But we can see that this may no longer hold when edge weights change. The example that I have here is that I've changed this edge weight cost from 6 to 1. And so now we can reach the red node, searching back through the graph by a new optimal path, coming down from this node here, which would make our new G value 5 instead. So this hasn't been preserved. And then these changes then propagate to our predecessors, because the costs for the predecessors are each dependent on the G value for their successor. And so when we hit a node, we have to propagate that change all the way back through the graph. So to do this efficiently, we take an A*-like approach where we update the lowest cost nodes first. And we don't expand a node until it is the next lowest cost. To help us do this, we're going to store an additional value. We'll call this RHS. Now, the meaning behind RHS, it comes from the term right-hand side, which in the paper where it was first introduced made more sense than it does so here. What you can think of your RHS value as is essentially your corrected G costs. When edge costs change, how G should be assigned so that it is correct for a given graph. And when your RHS value is not equal to your G value, that means that we have what is called a local inconsistency. So given the logic that your RHS value should be what your G value would be corrected to be, what would your RHS value be for this graph here?
Five?
5, yes. So this is the same graph that I presented previously, and I walked through how G should be 5. RHS should be 5 here. And what we're tracking is RHS and G differently. So G is what it should be, but we haven't updated G to be 5 yet. So we have two different types of local inconsistencies that we distinguish between. We have what we call local overconsistency, where G is greater than your RHS value. This is going to behave more similarly to Dijkstra's algorithm, where the value that we're associating to every given node now is higher than it should be, and we're relaxing down to the true value. However, we have a locally underconsistent case that we have to handle slightly differently. So now we're going to walk through updating and expanding nodes. What I mean by updating a node is recomputing the RHS value and then placing that node on the priority queue if that node is locally inconsistent. So to give an example here, I've changed this value, moving from 6 at the bottom to 1, and recomputing RHS as we did beforehand. Now we see that the node is locally inconsistent. In this case, it's locally underconsistent. And so we place that on the priority queue. The priority queue values are based on this new formula. This new formula essentially handles how we see G and RHS. In essence, we want to take the minimal value off of one of these so that we can handle it the first time that it will cause changes that propagate through the graph. And so this is essentially our ordering on our priority queue, which is essentially the same coupling that we saw for A star. But here we just had G of S replaced by the minimum of G of S and RHS of S. And so here, your minimum of G and RHS is 5, plus a heuristic leads to a total cost associated with this node of 9, 5. So we expand our nodes by then taking them off of the priority queue and changing G. Now I said here that we had a locally underconsistent node, and so we update this in much the way that we would expect. Your G values are relaxing down to your RHS values, and so we just set G to be equal to RHS. In this case, our node is now locally consistent, and it's going to stay that way. So can anyone think of some good reasons why I go through the process of changing RHS and keeping track of that new value, only to put that on the queue and then take it off again, instead of just recomputing what G of S should be in the first place? Does anyone have any ideas? What you can think of is that you're putting something on the queue, but if we update that value, immediately there are multiple nodes that could change the same node that we've just considered. By which I mean more changes as they propagate back through the graph could lead to changes in the RHS value of that specific node. And so what we would need to do if we recomputed G of S every time is put it on the queue, take it, or put it on the queue to signal that we're recomputing G of S, and do that recomputation. And then new changes could come, perform that again, do that again and again and again and again. And we want to avoid that situation. So what we're going to do is we're going to keep RHS as essentially a temp value that can be adjusted when it's in the queue. So when something is on the queue, it's on there once, and it can be updated and taken off, but we know when it's been taken off, that it's been taken off at the correct time and won't need to be handled again.
So, if I understand it correctly, so for example, if you had a single edge cost, edge weight change, then you could just do what you just said in terms of like, you could just update the thing and propagate to the predecessors, right?
Yeah, so if you knew for sure that nothing else was coming back down,
Okay.
then we could just do that change and propagate to all the predecessors because nothing upstream of that node is affecting it.
So am I understanding correctly? So you're basically running dynamic programming. So then, because you are even keeping the cost you go to the goal. And then what you're doing is every time you have an edge that changes to a value that could potentially make that node better than it was before. So if it changes the value of that node to something better than it was before,
yeah,
then basically, so you would change that node and then propagate and then queue all the predecessors of it, because those could be changed as well.
Yes.
And then, I mean, if those nodes do not change, you don't do anything. You remove them from the queue. If they also change to a bad value, then you keep propagating until you have nothing else to propagate.
Yeah, but we only do the propagation, or we queue changes that occur earlier in the graph, but we only actually perform the change, resetting the G value when it's expanded.
Okay, so and then the reason for that is for efficiency. When you have more than one edge changing,
yes.
So you could basically have multiple paths affecting the same node.
Yes.
And in this situation, so if you actually allow your changes to occur at multiple edges, that's when the importance of the queue comes.
That's exactly.
Which is exactly, it prevents you from redoing the same work over and over
That's
again.
exactly right,
Okay.
because if another change came through, then we put all the predecessors back on the queue again, and we do our updates for them as well. So we're avoiding that process.
And the queue also ensures that we're only updating by and I think Ben will cover it, but in the manner in which we terminate, we don't expand every node in the queue. We only expand those we need in order to find the shortest path, and then we retain the queue for the next search in case we need to update those in the next round of the search.
Right.
Oh, cool.
So I have to correct a mistake in my language that I said before. I said that the node in my examples that I gave before was under-consistent when it was in fact over-consistent. I apologize for that mistake. Over-consistency is the easy case that we're handling here, where when we expand that node, we have to take G of S and set that to be equal to the RHS value for expansion. And then we propagate that effect to all of the predecessors at that point, which means we update the predecessors and put those on the queue if it has an impact on them. This means that the node is now locally consistent and it's going to remain that way in that fashion. The under-consistent case, which was the opposite of what I showed, is the more difficult case. In this case, the old path cost was better than the new RHS value. RHS value has increased to above what G would be. In this case, we can no longer relax down to that G value from our Dijkstra's algorithm perspective. So we have to think of a new way to handle this. What we do is we essentially set our G value to be equal to infinity. And this is an extra step that's going to cause the node to go back on the queue an additional time. But what this mechanism assures is that that node goes back on the queue at most one additional time, which means that for D star Lite, we only ever examine any node at most twice on the queue. Once we've set G of S to be equal to infinity, then we can essentially relax down to the RHS value from the perspective that we had before. So we set G of S to be equal to infinity, and we update all the predecessors of S and S itself this time. As I was saying before, we need to put that node back on the queue so that we handle it when RHS has hit its minimal value. And this means that that node is now going to be locally consistent or over-consistent. And we handle over-consistency in the case that I showed before. So to give you an idea of how exactly this works, I'm showing an example here. We start off with this graph, and we introduce two changes. We have increased this edge cost to 5, and so RHS has now increased to a total of 10. But I've also changed a value here for edges that you can't see. But assume that the RHS value of this node has also changed to 10. So now we can put all of these nodes on the queue, ordered in this way, computed using the formula that we've seen before. We expand the node S1 first, and because it's under-consistent, we set G to be equal to infinity. Then we propagate to all predecessors and S1 itself, meaning those go back on the queue. Now, assuming that no changes of any relevance happened in these nodes, we recompute the cost for S1, which is now changed to 1410 because we're using the minimum of infinity and 10, which is 10 plus 4 for 14, going behind the node S2. Next, we expand this node S2, and because that was an over-consistent case, we can just set G to be equal to our RHS value. We then have to propagate that to its predecessors, which includes S1, which is updated its RHS value. So if we didn't do this, we wouldn't have handled this effect correctly. When we set our RHS value here, we then have to put this node back on the queue. So previously, S1 is already on the queue, but the effect has to be propagated to this node, which puts it on the queue again, which would mean adjusting the values, because RHS has been reduced by 1, both the costs here have been reduced by 1. Then we expand that node, we have an over-consistent case, we're setting G to be equal to RHS, and finally, we've completed our graph search problem. So now what we have to handle is an additional complication that occurs between several steps, tracking how our heuristics have changed. So we want to carry over our priority queue, which was what was mentioned previously, between our different searches as our start node moves. But the problem is that we're moving from our start node to a different point. Recall that our heuristic value is measured from any given node to the start node. So when our start node has changed, the heuristic value is not going to be the same value to the new start node. So we want what's already on the queue to be comparable to what is being computed for our new value, so we can use the math and the algebra that we've already done. So how we handle this is we introduce something called the key modifier. When we move from the previous start node, which here I indicated as S last, to the new start node, all the heuristics for an admissible heuristic are lowered by at most the heuristic from the last start node to the new start node. So now when we add new nodes to the queue, instead of subtracting that value from everything that's already on the queue, what we do is we just increase for all nodes that we put on the queue their values by this new modifier. Because essentially when we're taking things off of the queue, all that matters is the relative differences between the two. And so instead of subtracting a value from everything on the queue, adding that value to all new values that are put on the queue will achieve the same purpose. And so our key modifier is initialized to 0 at the start of the algorithm, and is increased every time that we update our start by this new value, by the heuristic between the last start node and the new start node. And then we update our total cost to include the addition of the key modifier for our F1 term. So now we've covered all of the D Lite algorithm basics. And we can essentially walk through the slide that I showed before with the math. So when we start, we initialize all of our G values to be equal to infinity and all of our RHS values to be equal to infinity except at the goal node. And that's to ensure that we always have a node to start from our search. We best first search from the goal node to the start node until that's locally consistent and expanded, which you now know what that means. And that signal that we have found our best path. We move according to our movement rule. And then if any of our edge costs have changed, we update our key modifier and update our RHS and Q positions for the source nodes of changed edge costs, meaning the nodes from which those edges originate. And then we simply repeat from 2, following best first search through the principles that I've walked you through for over-consistent and under-consistent nodes. And as a reminder down here, we always search by, or sort by this very long couplet of 2 values. So now we're going to walk through an example of D Lite algorithm.
Okay, so again, here's the pseudocode that Ben was just presenting. And we're going to go through a quick example with 5 nodes. So this isn't going to show all of the properties of why you would want to use incremental path planning, because when you have only 5 nodes, you're going to end up updating a lot of them a lot of the time. But after the example, you'll see how it makes more of a difference on a larger graph. So in this graph, we're going to have 5 nodes labeled A, B, C, D, and G is our goal node. The robot will start at node A, and its goal is to find the shortest path to node G, except that the graph might change as the robot goes through, or the robot might gain new information. So initially, the robot thinks that every node is available, and it knows that the path lengths are all 1, except for from D to G, the path length is 10. So this is a bidirectional graph. Every edge goes both directions, and the heuristic, as Ben described, will be with respect to the start node. In this case, we'll just say that the heuristic is the number of nodes to the start node, so we're ignoring the fact that this edge length is 10. So first we'll initialize all of the G and RHS values. So we have infinity at every node except for the goal node, which has an RHS value of 0. So this means that all of the nodes are currently locally consistent because their G and RHS values are the same except the goal node. So we put the goal node on the queue using the formula that was on Ben's slide, which I'll put here for reference. So the key is going to be these 2 terms. First we have the minimum of G and RHS plus the heuristic value plus the key modifier, which is initially 0. And then we have the second term, which is just the minimum of G and RHS. So you can see how we would get 3, 0 here, because the 3 comes from the heuristic and everything else is 0, so we're just adding a bunch of zeros. So that's everything that happens for the initialization. And now we have 1 node on the queue, so what do we dequeue first? This is an easy question. The 1 node on the queue, so we dequeue G. So we're going to update its G value. So as Ben said, the RHS value is sort of a look ahead. You can also think of RHS as being the shortest path that we've found so far, and G is the guaranteed shortest path to that node. So this one is trivial. The shortest path from this node to itself has length 0 because it's the same node. So now we're going to update the RHS values at its neighbors. So it has 2 neighbors, C and D, and in each case the RHS value will be the minimum. This is not actual math, but it's the minimum of the edge cost, well, the G value of a neighbor plus the edge cost, which is the same thing as the edge weight or the weight W So we have RHS is 10 here because it's the distance from G to D, and then it's 1, which is G to C. So again, we can calculate keys for those. So now we'll DQ another node. What should we DQ next?
C.
C, because it has a smaller key. So we DQ C, we update its G value. So this is saying now we know that the shortest path to C actually has length 1. And we can also compare this to the A-star algorithm by drawing a search tree. So in the beginning we had, here's our A-star. In the beginning we just had node G because we're searching from G backward through the goal. And then we expanded that to get C and D. And in A-star, we keep track of the path length to that node plus the heuristic at each node. So the path length to C was 1 plus the heuristic is 2, gave us a value of 3. So if we go back a moment, you can see, is that okay? Okay. So you can see that this 3 was the same as the first part of the key, and the path length 1 is the same as the second part of the key. And then similarly at D, we have the path length, which is 10, plus the heuristic 2 gave us 12. So this 12 is the 12 here, and then the 10 is the path length. And so you can see how if we were doing this the A-star way, you would also DQ C next. Okay, so now we DQ C, and we're going to update the RHS at its neighbors. So B is pretty simple. Previously its RHS was infinity. Now the shortest path to B that we found so far has length 2. So here we have B with a path length of 2 plus a heuristic of 1 gives us 3. But what about D? Previously its RHS value was 10, but do we now have a shorter path to D, given that we're expanding C? Or is 10 still the shortest path?
There is a shortest path through C.
Yeah, so now that we're expanding C, we see that you can actually get to D in only 2 units instead of 10 units, so that's better. So we'll update the RHS value to 2, and that means that we're going to change D's key accordingly. And the way that maps to A-star is, so here we have the path length is 2 plus the heuristic is 2 gives us 4. And the fact that we're changing the key to 4, 2 means that we're never going to expand this D because A-star uses an extended set. So it would always expand this D with a shorter cost before this one. So that's indicated by changing the key on the queue. So what do we do next? Which node do we DQ? B? Yeah, because it has the smaller key. So we'll DQ B, we'll update its G value, which is again saying that we know now that the shortest path to B is 2. So we DQ B, and then we expand it. How many neighbors does B have? 3. So we're actually expanding to all 3 of those neighbors. We have A, C, and D. Can you still see this? Okay. So at A, it's pretty simple. We have the RHS value is 3 because it's the shortest path through G, C, B to A. So that's 3 plus the heuristic 0 is 3. What about, oh, and then at C it doesn't change because you could go through B and back to C, but, oh, C should actually be on here, sorry. C should be on here because we don't want a loop in our path. Okay, so at D, can we do better than this path length of 2? No, because what happened was originally we had the path length of 10 through G, and then we had the path length of 2 through C, and this path through B is not as good. So we're going to keep the same RHS value and key at D. And we can see the analog in A star where we would have, if we did do G, C, B, D, we would have a path length of 3 plus the heuristic of 2 is 5. But we would never actually want to expand that D because it's not as good as this one. Okay, so now what do we DQ? Looks like we have 2 nodes on our queue currently. A. So we DQ A. That's where we were trying to get to because that's the current start node. So we set the G value to 3, which means that that's actually the shortest path. And we're done. We found the shortest path. Well, we're done except that the path might have to change. So one thing to notice here is that we never had to actually set D's G value. So it's possible maybe there's still a shorter path to D, but it doesn't matter. So now the robot will move to its next best place, which is B. And we'll update the heuristics accordingly because this is our new start node. So now, our heuristic is the number of nodes away from that green node. And we're keeping the same items on the queue from before. But we also have to update the key modifier. So now what happens is an obstacle appears. So there's an obstacle at C that the robot can now see because it's moved closer to node C, but it couldn't see it before. So now we're gonna indicate that by keeping all the edges but changing their weights to infinity. And that means that the robot could try to get to C, but it won't ever get there. So what we do next in the algorithm is we're going to update all of the RHS values associated with the source nodes of these edges. In this case, the edges go both directions, so it's all 4 of these nodes are affected by the infinities. So let's start with node C. What would be its new RHS value, given that RHS is the minimum from one of its neighbors to it of the G plus edge cost?
Infinity.
Infinity, because all of the edge costs going to C are infinity. So what would be the key? The tricky part here is the first part of the key is the minimum of G and RHS. So the minimum of G and RHS is 1.
So it'd be 3, 1. Yeah.
Yeah, 3, 1, because the minimum of G and RHS is G, which is 1, the heuristic is 1, and the key modifier is 1. Okay, how about node B? What's the new RHS value? So it has a neighbor here with G is infinity, a neighbor here with G is 1, except the edge length is infinity. And then this guy with G is 3.
So it's infinity 4.
4, yeah, because currently we still think that you can get to A in 3 units, so this is actually going to be 4. So this is one of the sillier things that D star does, but luckily it doesn't do this very much, so it doesn't actually really cost you much time. And then how about D, what would be the new RHS value?
RHS.
So it has 3 neighbors. This edge length is infinity, so that's useless. 3. This one has G is 0 plus 10 would be 10. Yeah, so this is the best one. G is 2 plus edge length of 1. So that would give us 3. So now do we DQ?
C.
C. So this is one of those tie-breaking cases where both of them have the first value is 3, but C has a better second value in its key. So we'll DQ C. Is this over or under consistent? So the definitions of over and under consistent that we had earlier, we had if G is greater than RHS, then that's over consistent, and we set G equal to RHS when we're updating G. So that was the case that we've seen so far. But then if G is less than RHS, it's under consistent, and we set G to infinity. So what is this?
Under consistent.
under consistent. So the reason intuitively why we're going to set g to infinity is because we're saying there's some sort of contradiction here. This 1 doesn't make any sense, it's less than the RHS value, so we're going to just reset g and sort of start over with this node. So we set that to infinity. And in this case, we don't actually need to add the node back onto the queue because it's now consistent, it's now locally consistent. So next we'll dequeue the one with the smallest key, which is b. B is also under consistent, so we're going to set its g value back to infinity. So this is sort of resetting the weird thing we did earlier that didn't make any sense. We're going to update its neighbor's RHS values. So what would be the new RHS value for A? Now that we know that we don't actually have a path to B. Infinity, yeah. And then how about the RHS value to D? Because currently D got its RHS value by going from A to B to D.
Ten.
10, yeah, because now the only way, RHS is 10. The key would have that 1 also. Is that right? Yeah, because currently the best path to D, and actually the best path to D, you can see, is from G to D, because you can't go through C anymore. So now we'll dequeue node A, because it has the smallest key. It was also under consistent, so we reset G to infinity. So we'll propagate that to its neighbors. And if we continue doing this, then we find, eventually we dequeue this node. And in this case, we had to dequeue everything, so now all the nodes are locally consistent. So what's the best path that we found from B to the goal?
BDG.
BDG, and it's also the only path in this case. Oh, we had to update B's neighbors. Okay, so here's our new shortest path. So now the robot will move to node D. But now what's going to happen, again we update our heuristics, but now what happens is it turns out it's a moving obstacle and it starts following the robot. So now the obstacle is moved to there. So as humans we can see that obviously the shortest path is through C, but the algorithm doesn't know this yet. So what would we do next? So we just updated our edge weights. So now all of the edges to B are infinity, but some of the edges to C are no longer infinity. So we need to update the RHS values accordingly. So we'll update all of the RHS values that were affected by this change. In this case, G's RHS value never changes because the distance from G to itself is always 0. And this one doesn't change because we still use the G value here. Okay, so now again we can start dequeuing and planning a new path. So we'll dequeue this node, we'll propagate to its neighbors, dequeue that one, update the RHS values. But in this case, we don't, let me go back a step. So we dequeue this node and we updated its G value, but we don't actually need to continue dequeuing things. We should, oh, this RHS value should be updated. Oh, it is updated. Why is this RHS infinity?
All edges into it are infinity.
Yeah, all edges into it are infinity, you can't get there. But we don't actually have to bother expanding B because we've already found the shortest path. So this gives you sort of a hint at when D star might be efficient, because even if there were a whole bunch of nodes over there, we wouldn't need to consider them because we found the shortest path. So now the robot can move up to C. And let's say the obstacle chases the robot again. Do we need to plan a new path? No, so intuitively we don't because the obstacle is not in the way of our current best path. But we can also see algorithmically why that's the case. So first we'll update all of our RHS values accordingly because we've changed all of the edge weights. But the reason why algorithmically why we don't actually need to consider any of these changed values is because this node has the smallest key, which means that this is a node that has the shortest path to G anyway. Well, it has a smaller key than all of the other nodes that are on the queue. So dequeuing things wouldn't actually help us find a shorter path. So the robot can move to the goal, and we've succeeded. Any questions on that? Okay, so now Ben will talk about sometimes when you would want to use incremental path planning other than this 5-node graph.
Thanks. So as Jess said, there are sometimes good reasons to use incremental path planning, but there are also good reasons not to in certain circumstances. In certain circumstances, we can actually formulate graph problems where the problem is worse by using incremental path planning. Remember that I said that D Lite puts any node on the queue at most twice. And so we can compare that to A or something like that does full replanning whenever a search occurs. But that puts every node on the search queue at most once. So D Lite is most beneficial when putting nodes on the queue potentially more than once leads to less nodes being examined overall. So here, this is essentially what I've just said. So A might perform better for certain problems if we only have to consider a small amount of nodes anyway. So putting nodes on the graph twice would actually lead to more expansions. And so to get an intuition behind why that might occur if changes are close to the start node, I want to show you an example here. So here we're actually showing an example that's derived from LPA star. So we're searching forwards here from the start node to the goal node. And that's just a different reformulation, so don't let that confuse you too much. When we walk forward through A star, with a good heuristic, we might move directly from the start node to the goal node and find that path. Now, if a change occurs somewhere upstream of the start node, when we're replanning, we essentially have to replan the sections that are beyond the change that's occurred. So everything that's here, to an extent, is relatively insensitive to this change. It could occur that we would have to take an entirely different route, but for the most part, it's likely that changes are going to couple to our existing path in some form. And so we have an efficient search that will just go around from the path that we've already planned to our goal node. And so in this sense, we have an example where incremental path planning would be fairly efficient. In this case, which is a different one, we introduce an obstacle very near our start node. And this means that most of our existing path is destroyed. So when we search out from our start node to our goal node, we have to do a lot of recomputation from scratch. And so an incremental path searching algorithm is going to have to undo all the search that we've already done, and then search through almost the entirety of the graph again. So intuitively, in this case, just restarting with A star from a blank slate, which would search directly down to the goal, instead of doing reparations that would send us in the wrong path, would be a better idea in this case. So since we're planning from the start to the goal, in this example that we're showing, it's worse to use incremental path planning algorithms when your changes happen near your start node. From something like D Lite, we search back from the goal node to the start node. It's better if changes occur nearer to the start node, which for our vehicles that we normally see that have limited sensor horizons is what's going to occur in the most case. So in those type of situations, incremental path planning is going to be very efficient.
So I understand how this could be a problem for LPA star and D Lite, where we're finding a single path, where you have like a single source, single destination, or something like that. But what if it's like incremental all pairs shortest paths, where you've computed? Would you? I assume you wouldn't experience the same problem if your algorithm was computing shortest paths between all pairs of nodes in the graph.
Yeah, if it already exists. Well, that depends. I mean, when you're redoing recomputation between all nodes in the path, it depends if our obstacle has changed the neighbors of the node that we want to consider. And by that I mean, imagine in this graph we've computed the paths and the path costs to get from every single node to every single other node. Now, if introducing an obstacle here only changed the path cost to get from our start node to our goal node, for example, then replanning that specific pair of paths from the start node to the goal node would use data that already exists from the other nodes to the goal node. We already have that. But if introducing an obstacle would cause changes throughout the entire graph, then we can potentially create what would have to be a very well-connected graph, where, again, incremental path planning would probably perform worse in that case.
Yeah, right. Yeah, so you could still end up in the same situation.
Yeah. Now, these algorithms are very interesting because they allow for some extensions that allow us to do some very different things quite easily. One example is greedy mapping, in terms of how can we design an algorithm using what we know about incremental path planning to hit every single node on our graph. And what we do is that we introduce a faux goal node, essentially a node that doesn't exist, that we can never reach. And we add to our initial belief state or our initial understanding of the graph connections between all nodes to this faux goal node. Now, it's false in the sense that whenever we move our start node to one of the nodes that we've examined before, what happens in terms of the changes of the edge costs is removing that edge that connected that node to the goal node. So what this means in principle is that our poor vehicle can never reach the goal node. Whenever it reaches a node that it thinks it can get to the goal node from, that path disappears. But what that causes it to do is when it's replanning, it finds a path to a node that we haven't visited before because it thinks that there is a path that leads from that node to the goal node. And so this means that it's efficiently replanning a route from its current understanding to a node that it hasn't examined before. And so we can apply something like D Lite or LPA star with this formalism in order to search through the graph in its entirety and make sure that in a greedily efficient manner we hit every single node in the graph.
Is this some sort of like approximation to the TSP problem, like the traveling salesman's problem?
I'm not very familiar with the TSP problem.
You are a traveling salesman and you try to cover all the cities and try to come up with a route that is the most efficient. And you usually try to visit every node, every city only once.
Okay, then in that case, yes, it's not going to be globally efficient. But as you said, it's going to be an approximation for it. In a sense, from each node that you visited, you're searching for the next best choice. So it's possible you can corner yourself, but it's a way that we use what we've already implemented and the methods that we've already established to tackle a different type of problem.
And how does it is usually if you have a strategy which is visit the closest unvisited node instead of like making this whole incremental path planning stuff. If your policy is always go to the closest unvisited node, how worse does that get compared to this?
I think it would behave quite similarly. What we're just trying to show here is that we can implement that problem as an extension of this algorithm. It may be an inefficient way to do it.
You probably like zigzag a lot more.
Also, if you're just going to the nearest connected node, if you corner yourself, as we showed here, then you could potentially run into issues if your algorithm doesn't then do an extended search forward. If it only considers nodes in its immediate neighborhood that it hasn't visited, once it corners itself, it doesn't know where to go.
Well, just keep going through the graph until you hit the next unvisited node, assuming that you know how many locations you have to visit.
Sort of like a random walk type approach?
Well, I mean, kind of like the greedy version of it. You kind of like, you start from a node, and then you keep searching, you see, what is the next unvisited node, and you pick that. Kind of like usually if you have like some audit optimization, it's usually that. You see what you have covered, you see what's the next best move, you make that move, and you're done. But I mean, this doesn't look, the objective here doesn't seem to be submodular in the sense that you don't have diminishing gains.
Right.
So you probably don't have the same guarantees. So it probably doesn't make much sense to compare it.
No.
Okay, cool.
Yeah, this basically ensures you're going to find the shortest path back to the next unvisited node, I guess.
Yeah.
We also can use these incremental path planning algorithms for anytime planners. And the benefit of an anytime planner is that we quickly reach a plan which is suboptimal. And then from there, we are repairing this plan to approach optimality. And this is useful in the real world where you want to get a solution that comes out quickly, and we want to start along our solution and then repair it as we go. And once we've started moving to save some more time if your reparations might lead to small changes or that type of thing. And this can be handled quite efficiently using an incremental path planner. So what happens is we apply something, idea called inflated heuristics. And so these inflated heuristics are essentially increasing our heuristic values that exist on our graph, in our true graph, by a constant scale factor. And this is typically very large, so differences in heuristics become very large. This means that once we start along a path, we continue along it. And that causes us to very quickly find the first path that actually works. Then we can view reducing those heuristics back to their original values as essentially a form of changing our H-weight costs. As a form of replanning. And then by applying the principles of an incremental planner, we can efficiently use the data that we already have in order to perform this search and repair our solution as we go. Finally, we want to make explicit to you guys how we can actually apply these algorithms to mobile robotics. Because it may not immediately be clear. How we go from a full space to a graph. Joe touched on this kind of briefly when we talked about how we might discretize the world, but we want to give you guys some ideas of how we might do this cleverly. So in order to build a graph system out of our world state, we differentiate between holonomic systems and non-holonomic systems, which their difference is just in terms of whether your constraints are differential in nature or not. Then we're going to outline 3 methods here very briefly: cell decomposition, using a visibility graph, and sampling-based construction methods. So for cell decomposition methods, we might do what you would expect, take the free space in this region and split it up into various different cells. And each of those cells is going to represent a node in our graph. And how we can do this is we split the region up based on each of the vertices of our obstacles. So we draw a line vertically, from each of our vertices that goes in the direction away from the obstacle. So at the top here, it's going up and out of the obstacle, but in the lower left corner there, both up and down don't intersect the obstacle, so we draw that in its entirety. So we can continue this throughout the entirety of the state space, and then we can attribute to each essentially cell that we've defined through these regions a single point that represents the midpoint of that cell, which is going to be our graph node, because we attribute a single set of coordinates to each of our graph nodes. And we also, to make sure that our transitions between these cells are consistent, add additional nodes at the midpoint of each of these lines that we've drawn, where we make the distinction that from here we've actually drawn 2 lines. So we draw the midpoint between all of those. This allows us to essentially create a graph throughout the entire system, and we connect each each node at the center of any given cell to the nodes that are on the boundary of any given cell. This allows us to create a full graph through the system that we can move through, guaranteeing that none of these paths, if we follow them exactly, collide with the obstacles. Now this works in environments where the obstacles are 2D polygons and the path is far from optimal, as we can see, but we can plan an optimal path over the graph that we have defined. And this only works on holonomic systems. We can also define what is called a visibility graph, where we essentially draw a boundary between both our vehicle down there in the bottom left and boundaries around our obstacles. These boundaries are sufficiently sized so that if the center of the vehicle that we're defining is along the extended edge of the obstacle, that the vehicle will not collide with that obstacle. Then for each of the vertices of the extended boundary that we've defined, we add in a new node, and we draw all lines between all nodes which can be connected without intersecting the extended obstacles, which we've drawn here. And this leads to a graph that we can again plan over. This again works in environments where the obstacles are 2D polygons, but what's nice about this system is that we do get an optimal path, provided that we assume that our extension of the robot itself is valid or doesn't add too much, isn't too excessive of a constraint. Finally, going back to some of the random sampling methods that we mentioned at the very beginning of this lecture, we can introduce sampling-based roadmap construction, wherein we choose nodes randomly or deterministically throughout our environment. The difference here, though, is that we then create a graph out of this system, and then we reason over that graph using something like an incremental path planning algorithm. And so when we create that graph after we've sampled, we can use the k nearest neighbors of each node, or we can connect each node to every node within a certain radius, which is what we've drawn here. Finally, in order to actually move between nodes, we need to have some knowledge about the dynamics of the vehicle, which is what we're discussing here. And one method that we can do this for non-holonomic systems is we can distinguish between different paths that use turning right, turning left, and traveling in straight lines. It turns out that the shortest path between 2 points can be defined using one of these systems. And so we just have to search over a finite number of options in order to find the best path that can connect any two nodes. Hopefully that has given you some intuition into how you can apply these systems and incremental path planning to some of your systems. Are there any questions?